Good afternoon, everyone. Today we're presenting our Capstone project. It's called Piezoelectric Wireless Power Transfer Charger. The name of it, we wanted to give some credit to the component that we use, the Piezoelectric. So this is the outline that we want to try to cover as much as we can and touch on some of the points. Isabella Kokolski. I'm the project manager. Basically, I was in charge of the piezoelectric research. And
my name is Hudi Seidu. I'm the hardware specialist and also in charge of the wireless power transfer research.
So the project motivation comes from the idea that, just a quick question, by showing hands, how many of you have a charger right now? Okay, so probably about 10. 5 to 6, right? So everyone always, and our devices, the small device that we use as an example today in the project is a cell phone. So it's running out of battery all day, most of the day. So you have to run to a charger or outlet to power it. So that's the idea behind it. But more than that is, if we take it to another magnitude, it's about 3.6 million people around the world that don't have or have partial access to electricity. Also, through global change, warming climate, we have recently Hurricane Michael in down south Florida. It took about 6 months, and some people don't even have power up to date. So that's the main idea behind our project.
Also, we already have some of the devices in the market. But the device in the market is based on kinetic energy in order to charge it. So ours, we are trying to create something new, which is the wireless transfer charger, where we are going to put it with whilst we are working, and also the work on is also charging. The one you see here is the one that the Red Cross is using to charge their portable device in case of power outage. Okay, this is our main idea. Our main idea is to generate power from a piezo sensor, where energy is, where power is collected at the terminal of the piezo sensor, and then wireless charger transfer is going to be based on electromagnetic induction in order to transfer power from one place to another.
So in other words, the main idea is that we're trying to do is to create power through walking. Next is a small video to understand a little bit about piezoelectricity.
Piezoelectric material made of silicon and oxygen. The oxygens have a slight negative charge, and silicons have a slight positive, creating a separation of charge, or a dipole, along each bond. Normally, these dipoles cancel each other out, so there's no net separation of charge in the unit size. But if a quartz crystal is squeezed along a certain direction, the atoms shift. Because of the resulting asymmetry in charge distribution, the dipoles no longer cancel each other out. The stretch cell ends up with a net negative charge on one side and a net positive on the other. This charge imbalance is repeated all the way through the material, and opposite charges collect on opposite faces of the crystal. This results in a voltage that can drive electricity through a circuit. Piezoelectric materials can have different structures, but what they all have in common is unit cells which lack a center of symmetry. And the stronger the compression on piezoelectric materials, the larger the voltage generated. Stretch the crystal instead, and the voltage will switch, making current flow the other way.
So the social impact that we're thinking about is, it will be this is no targeting, we're not aiming to the regular people like close to the city. Now we have kiosks in the middle of all New York. We're trying to aim people that don't have access to electricity. We're talking about remote villages and around the world, Inspire and Wood was a veteran, so they have to carry a lot of equipment, goggles, GPS tracker, cell phones, stuff like that. Flashlights during natural disaster, Or there is about 40% of hikers that get lost in the middle of nowhere, and they don't even have access to make a small phone call. So these will make, we thinking that will make such a difference.
Our system has been designed and also divided into 3 subsystems. First of all, the first system is generation and transmission, and also the second system is also the resonance couple system. And then the last one is receiving and also charging circuits.
This is the breakdown of the flow chart of the project, just the schematic that we kind of put in blocks.
This is the theory that we built on it in order to design our system. First of all, when it comes to the piezo arrangement, we arrange it in series and also in parallel in order to take away the internal resistance of each sensor. Based on it, we're able to come out for high voltage. And also, rectifier circuit we based on the calculation of the voltage drop on each diode. So we're able to subtract 0.5 times 2 from the full wave rectifier, and we get our voltage, which is 28.6. And we calculate the peak impedance, peak inverse voltage to make sure that our rectifier can withstand our rectifier can withstand inverse voltage. And also, when it comes to the inverter too, we use this frequency equation in order to come out with the switching mode of the MOSFETs. And then we go ahead and calculate the period and also the gate current that we need in order to trip the MOSFETs. We also use interlink boost converter, and as you can see, this is the equation that we use to come out for our parameters.
So just want to make sure we both electrical about to graduate as electrical engineers, so we wanted to implement our own design, and we did extensive research into the MATLAB Simulink and all the devices, the small devices that we have learned, electronics, power electronics. So we came up with this design and MATLAB. It was functional. This is the output, the simulation that we get in the right side is the output that we will put into the charging unit. The left side is shown, the top one is the voltage that comes out from the piezoelectric generator, and it has to be inverted to become to DC. And then at the bottom is the wireless power transfer. It only transfers AC to AC, so we needed to convert it back to AC.
This is our hardware design. As you can see the various components in the hardware design. First of all, we have the piezo rectification circuits, and also a capacitor, and also we have the inverter, and then we also have the wireless circuits. After wireless circuit, it goes back to the rectifier again, and then through the boost converter. When it comes to testing, we make sure that we test every component before implementing it. So, first of all, we carry a test on the piezo sensor. We carry out continuity test to make sure that there is no short circuit in the piezo. And also, we also compress on the piezo sensor to make sure that voltage is generated at output. And the diode and the full wave rectifier we carry out a continuity test, and also we measure the voltage across the output, where we use multimeter in order to measure the voltage output.
This is the wireless power transfer system. What you guys seeing right now is a custom made. We came up with all the calculations, but we're going to explain a little bit more later. But basically was too bulky, and the purpose of our project is to be something practical, something easy to carry, something easy to use. So this is custom made. This is what the company sent us back. But this is the features and the calculation that we got.
We carried out a unit test on the DC to DC boost converter. We make sure that we supply one volt so that we can get output of 5 volts. This shows that our DC to DC boost converter is working. As you can see, there is an LED on it. When there is a power passing through it, the LED will indicate on, which shows that it's working.
So as last semester, we came up with a couple versions. We through our research to the development, the first two on top were the first versions that we got. Clearly, it didn't work out, so that's why it's called first version. And the bottom is the wireless power transfer. Again, it started becoming a little bulkier than we expected, so that's why we decided to send our design to a custom-made PCB.
This is our hardware implementation and also integrated tests. First of all, we carry a test on the overall piezo arrangement. We connect LED at the output of the piezo, and then we put pressure on the piezo arrangement. And we were able to get some power output. As you can see, the LED is indicating that our system is working.
This is the integration test of the wireless power transfer, the transmitter, the receiver. They both, because initially we got two different ones and they were not working. So again, it has a LED. It doesn't show these pictures, but you guys want to see it in the demonstration. This is the integration of the wireless power transfer working. The LED is showing that it's actually transferring power. Again, this is the booster of the integration. It has also an LED, but it wasn't until we complete the whole project to able to see that actually it's boosting the voltage. This is just a couple of pictures that we took through the process of the implementation and how a user will be aware of it. Acceptance test. In this case, actually, in the last minute we had a little challenge that our project wasn't working. It was working, but then it started dysfunctional. It burned out. So the acceptance test made us realize what we were doing wrong, what the polarity was the problem. So as a good engineer, we had backup.
This is our project completion and also feature work. Based on our project, we were able to overcome our challenges. Like we order some components. When the components came, it was defective, so we have to send it back. And also, we carried out a test. During the test, our board got bent, so we have to make sure that we also develop a new one. What is coming up? Okay, we are trying to improve our project. Even though we haven't finished everything yet, we are trying to make sure that we improve it. Even what we are doing our masters, we can do it as well as our time, so that we can improve it in order to add knowledge to ourselves.
So just to add up on Wood's explanation, as two members of the group, it kind of put a lot of stress on us, and to overcome our challenges, like ordering new components, putting them together, arranging schedules, time management, and all that stuff became it actually makes us realize that a lot more skills that an engineer should have. This is a little project demonstration. Initially has sound, but now the background it's just no proper. So I'm just gonna run it and I'm gonna explain as it goes.
This is how the project is gonna look like. As you can see, that's the piezoelectric sensor which goes inside the shoe, and it will be charging the battery, and the battery will supply power to the wireless circuit. And the wireless circuit will also take it to the boost converter, then to the mobile charging unit. As you can see, that's the demonstration of the piezo sensor.
That's the wireless power transfer, and that's the charging unit.
At this stage, it's not connected yet. As you can see, the receiver and then the transmitter are separate.
You guys will see in the next slide.
At this stage, the wireless circuit has been connected. That there's some connection between the two wireless circuits. I'm going to compress on it, and you can see the battery is charging through the rectifier. And we are going to bring the two circuits into contact. And this will light the DC to DC boost converter. That's the transmitter. That's the receiver too. So bringing it together, it will light the LED on the boost converter. I hope it's
So right now I'm going to demonstrate to you how our system is going to look like. First of all, we are going to put this on the machine. And I'm walking to grab voltage. So by doing this, I get the Capstone design through the rectifier. At least we have to walk 56 steps in order to get 26 volts the whole system. So that is allowed to do everything. It looks like a faster side. Okay, let me see if okay, so as you can see, after connecting the two wireless systems, we are getting power through the DC motor and the screen connected to the robot. So as you can see, the robot is charging possible.
Actually, we have a problem here. We cannot separate the two circuits more than 10 centimeters. So we have to keep it less than 10 centimeters. Sometimes we cannot even, take it beyond beyond 5 centimeters. So the wireless circuit is a problem for us. I think there has been a lot of research going on trying to transfer power from one circuit to another without the wire. So I think we were able to do our best in order to make sure that power is being transferred from one place to another through electromagnetic induction. Okay. This is how the person is going to wear it. And then as you can see, the piezoelectric sensor has been put into the shoe, and then the person will be working while charging his phone. Thank you.
This is the demonstration.
It's a video, right?
This is how the system is working. We are trying to modernize it by attaching this one, but by making sure that the cable is backed by a leading. So as you can see, we are walking.
Actually, you have to walk 56 times in order to get 26 volts. And then the 26 volts is not constant. It's not coming. So because if you charge a battery, the battery can drain so easy.
How they change. As you can see, it's charging, right? This is the charging application, right? How we go to charge. So we can use this one to charge any portable device. The electric one can use it to charge their communication device. As you can see, this one is charging. So, this house is going to look like it, but we are trying to work on this portable. That's what we want to demonstrate to you.
Okay, so our project still has some work to be done. Our biggest challenge was the wireless power transfer. We tried this idea to bring it as a new, different from other competitors and more sort of originality, but unfortunately the distance has to keep to a minimum in order to actually transfer power. So kind of that was the biggest challenge.
Actually, this is the cost that we spend on the project. And after this one, we have to make sure that we send our specification to a company so that they can build it portable for us so that we can implement it. So we spend this money on it and at the same time sending money to the company to build it for us. This is our code standard and then constraint. We base our code based on the IEEE and also some of the military standard.
This is the code of ethics that we all use as a main support. And the solution that we got is we try to combine all the constraints, the standards, and the IEEE to come up to try to satisfy all of them. And this is a reference. Okay, thank you.
Charge a battery? I couldn't tell from the video, it actually charged
It
the
did
battery itself.
Yes, it did charge, but again, we wanted to bring the new idea of the wireless power transfer, inspired actually on our power system that we took last year of the transformer idea. So, but it took us, it discharged very quickly, something that we didn't think of, and it takes about 50, 60 steps to only last for like 2 minutes or 3. So it's still underwater. Any other questions? Yes.
Do you know how many steps it would take to charge an entire phone about?
She just said 56 steps in order to get 21 volts.
So do you know how many that would be to charge like an entire phone or like an entire battery or something?
That's
It all depends on the phone, right? Like phone, for instance, we have one arm, 5 volts in order to charge it. Right? So it all depends on the capacitor, how much the capacitor is going to stay, also how much are you going to keep on working.
That's another issue that we find out. Different phones require different voltage, and we didn't think of that. So my phone was charging perfect, but an iPhone wasn't charging.
But if you are looking for the time, right, you can divide the energy by the work. You can divide the energy by number of steps. You can get the time.
Any other questions? Sure.
Did you try charging directly rather than wirelessly? Just charge the phone without going through the wire?
Yes, please. Yes, please. It's charging all right.
Is that better?
Yes. But we are trying to bring something new. Like
So
learn
that was
something
a
new.
big part of our project, the wireless power transfer, that's why. But it did charge, directly it will work as a regular charger. But the distance, we realized that it loses a lot of power through the wireless power.
And also we realized that whilst working, the two circuits is not going to stay in contact. It will be moving. So there will be flux.
Right, the distance and the movement of the user, it influence, it makes the losses increase immediately, and it makes the battery to drain. So it doesn't actually charge, so that's why the distance has to stay at minimum. Any other question? Thank you for listening.